Okay. Welcome, people of Earth, to day 22 of Advent of Code. Um, Turn off my noisemaker. Um, we just have a couple of minutes. Yesterday, I was pretty happy with how yesterday went. Uh, I, in both parts, I had minor bugs in the code that needed to be fixed. And it seems like I might have had a chance at the leaderboard if I hadn't had either of those issues. But that, at least at like my speed, that really is the difference. You have to kind of hit it flawlessly to get a chance at the leaderboard. But actually coming up with like the trick to part two only took me a couple of minutes, which is what you're going for. Um, because I guess there are two kinds of puzzles in Advent of Code. One is just kind of engineering, where it's kind of obvious what you have to do. You just have to put it all together. And like the hard ones of that form tend to be like in prior years. There have been these like simulation things where you've got, I don't know, mine carts on ASCII, rails, or I think one was robots or elves moving around according to a bunch of rules, and you just had to simulate a bunch of steps until they all bumped into each other or something. And those things, it's pretty, there's no trick to it. You just have to go through all the stuff, and you either have to nail it without making any mistakes, or do enough kind of engineering-y things that you can track down your mistakes easily and quickly. Given that it's a programming contest, I tend to shoot for the first. But um, um, but then the second kind of problem is where it requires some insight or some trick, and those are very satisfying when you come up with a good approach, but are really frustrating when you just are not getting it. And I did. There was one problem one year that I couldn't figure out, and I gave up on the entire event, and I came back. 6 months later or something, and it was still a slog to figure out. Eventually, I got there, but it was, yeah, it happens. It happens. So, anyway, I admit I'm still hoping for a relatively short night tonight because I'm tired. Um, but let's see how it goes. So we don't need any of this. So this is where we're putting our code for tonight. And the dog is already asking to go out, which is not a good sign. So again, we'll just have to do this quickly. Yeah. Okay, here we go. It looks like there will be some parsing, won't there? Yeah. Okay, so let's. Oh, we might as well just write our parser, mightn't we? Okay. Um, uh, and what should we do first? Um, place 0, 1, 2, 3. 0, 0, 1, 2, yeah. Place 3. Um, split. Okay, we already have syntax errors apparently because, oh, how's that? Any better? Yeah, okay, let's see how we're doing there. Okay, that looks good. And it's always X, Y, Z, so there's no real information in that. So, slice 0, 1, 2. Okay, we should move this. And 2. Are we getting there? Okay, so now we have the two numbers. Map. Another. So now we have. Oh, that didn't do it. Okay, what were not numbers? Something about this couldn't parse as an. Oh, equals. Oh, hold on. Those are all ons, and there are offs as well. Ooh, no, and we need to know that. Oh, God. Ugh. Curses! So, instead, damn it, we were so close. So let's start by splitting on. Actually, if we just do a white space split. If we do a white space split. Okay, so okay, so what? I hate it when my stuff rattles. What is rattling today? I think we got it. 0, 0. Okay. 0, 1. Okay, we split the second part on comma. And then okay. And then we chop off the first. Okay. Okay. I don't know about this indentation, but 1, 2. Right. Okay, what's going wrong here? Bool on. No. Bool on. Oh. Swift. Oh, a whole bunch. What's going on? Oh. Oh no. What am I doing? Okay. Print. Notes. These are okay. We're parsed. Okay, now let's get moving. What are we up to? Like it's 100,000 in each direction. 200,000. Can we blah 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 blah? Yes. Okay. Okay. So what is the actual thing? Whether to turn everything on or off. Okay. Second turns on. Okay, so let's. I don't know. I can't be bothered to think of the best representation. We probably could actually build it, but I'm lazy. So, um, um, okay. So, um, da, 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 um, um, okay, so we'll just keep track of which lights are on. Okay, in, and this is, oh, come on, where'd my shell go? Yes, it's two-dimensional array. In num 0, 0, 0. One. And our slow editing is definitely costing us places, because I wouldn't be surprised if other people had finished the first part by now, because this isn't a terribly complicated problem. Do, 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 do. Okay, before we do the turn off, which is symmetric but with a remove, let's just make sure that this does something. Trailing closure is confusable on line 22. Why did it hang? Ooh, there might have been a very big, ooh, no? Ooh, I worry that something was too big. That is a shame, which would mean we needed to do another representation if it just hangs like that. What is confusable? Line 22. What? Trailing for L lines map. we'll leave that warning. I forget what the syntax is. So this hangs at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20. So 20 lines in, come on, where is my input? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yes, now suddenly we're doing 12. Oh, yeah, because these are all multiplied together. Oh, there goes this. So we really do need a representation. Okay, let's figure out. So what are we trying to accomplish with this? Considering only cubes in the region, how many cubes? Only cubes in the region there? Okay. Okay. Min. -50. X. 50. Yeah. Okay. The second part might need a better representation, but the first part we can just be super lazy. Okay. See, it's a good thing we didn't do our remove, because then we'd have twice as much editing to do, and oh, you're done. So now what happens? It's still quite... Wait, that all seems quite slow. What did our input look like? On count. 0.34. 50, 50. If turn on. 0, 0. That all seems a little suspicious to me. That doesn't look like the right output at all. What is going on here? Yeah. I'm at a loss. On. No, so... Yeah, okay. Come on. Oh, these are backwards. Of course they are. I still don't quite understand what was happening there, but let's just give it another go. Ooh. Oh. Oh God. No, start X and finish X because it's inclusive, right? right? This is our magic. So four. Yeah, okay. The word. Yeah, it's not really much fun when we take so long to do simple work, you know? Oh, okay. And really, all this could have been done by search and replace, but I kind of want. I still don't really trust search and replace for this stuff. Um, maybe that's just me. Okay. And then the F, and the F turn on. So, how are we doing now? Well, it does the number ever change? Yeah. Okay. Oh, and we need to do the turn off, right? Um, else. We just do all the same thing. We could write a function that that takes a closure, um, and executes it in the middle of this uh, block. Um, but that would take more time than cut and paste reuse, wouldn't it? So, and what is it? Do we want the number of lights that are on? How many cube? Okay. Do okay. Do, do, do. If two. Can't make up a mind how to name my variables. What? Out, out. Ugh. Should have changed the other one, I guess. Okay, come on. Wait, where did it? Out? It. Hmm. Really? That strikes me as very suspicious. Doesn't it seem suspicious to you? Well, we can take a minute. Oh, okay, fair enough. Not as suspicious as I thought. Okay, starting with all cubes off and for all cubes. Yeah. Ah, yes. Okay, so now we can't just do our region. So a lot of the code we wrote for part one is useless now. Maybe all of it. So, how are we gonna do this? Um, um, there's actually a patented algorithm that I think you could use here. But I think no, the patent expired because it's a very old bitmap thing. Um, so, but there. Okay, what are we doing? Auto representation. So we can find, right, we can find cubes within us because we can keep the upper corner of every cube. So we can find the cubes we intersect with. Find all the cubes we intersect with. So we'll make a list of all cubes, right? But um, let's okay, because all this code is going away. I should have realized. In fact, I did kind of realize, but I wanted the part one. So, so um, equals. Let's do no. Let's do a um, map. Well, what are we doing? Well, first we might as well just create the thing of cube. Then we'll work out how to do it. So it's just going to be an array of point three point threes, right? So oh nah cubes. Like I say, I haven't actually thought through my algorithm yet. So this is really just trying to give myself some time to think. Do, 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 do. Oh, no. What we need are... So, 0.3. And then another 0.3. And then we close that. We close that. We close that. But this is... Um, I don't know if you can use a conditional for an L value, but that only cost us a few seconds. Okay, get rid of all this. This is just bothering us, right? So now, assuming this works, we will just have to do a little bit of. Oh, it doesn't work though. Why doesn't it work? On cubes, yeah, yes. You're very right about that, Swift. You win. Yeah, okay. 317 and 103. So neither of those are very big numbers. So, I never do spatial things. This is going to take me a while to figure it out. So, we want to find all of the that's why we didn't need our stupid loop the second time through. We were only doing 50 to 50, so our initial count worked. So that was a complete waste, the last few lines of our part one solution. Okay, sorry. It took me a second to figure that out. Okay, so now we have all these cubes. We could sort them by, top left corners and so forth. So we can put them in an order. And then we can find intersecting cubes. We can break them down into. Oh, but the order actually matters, doesn't it? Of course it matters. So we need to do them one at a time in a way that simplifies our search space, right? So if we have an on cube and then we have another on cube. So if we have a third on cube, then we can break that down into 3 additional on cubes. Okay. Oh, but and because we've split these up, so even this data structure isn't right. So what we really need is just this, right? Yeah. So we don't need any of this. It's just cubes append. Yeah, okay. I've done a lot of work without actually thinking through my solution here. Okay, 420 cubes. So we're going to create a bunch of inversion points. Inversion points? Is that the right solution here? So we say everything below and to the right of an inversion point is on, right? Inversion point there. So we could just make it a bunch of inversion points because I know how to, when you turn something on, I think I know how to modify, turn something on or turn something off. Or we could do it as a bunch of squares. This is taking me a long time to work out. And the trouble is, it's a standard bitmap thing, so anyone who has already thought it out in the previous 10 years of their life will probably have nailed this. But anyway, it's not about the competition. So, we have a square there. I suppose we have a rectangle. We turn on another rectangle. Yeah, so we'll just have a bunch of non-overlapping on rectangles. That's what we're going to do. So we're non-overlapping on. New. Okay. Well, we see. We didn't even need to create these cubes. We could just done it in the darn loop, right? So, but so yes, all the code we've written so far for part 2 has just been a waste of time. Okay. So, but we really want to sort new, right? It doesn't matter. There aren't going to be that many, so we can just scan it, right? Can we scan it? So when do two things overlap? Can we just 100 times 100? So we can just do it for all of them. Can we just do every pair of cubes that we have? They're not actually cubes, they're cuboids, right? I've taken like 20 minutes just not thinking the second part through. So, okay. And, and what does it return? It returns an array of so how can two overlap? They can, a point can be above. Yes, it can be. Okay. Okay, so A has the lower x coordinate, right? So, um, um, it's very hard to draw things in 3 dimensions on a piece of paper. So lower x coordinate, then the y coordinate. Um, B, y. Uh, wait, if x less than 1x. Well, no, it's greater than or equal to a1x. Um, because they don't overlap, right? Okay, so they overlap in 1 dimension. Now we're saying, um, if b 0 y b0. Okay. So then, um, I don't know how to comment, how to talk this through while I'm doing it because I'm thinking. What I'm trying to I, I, maybe I shouldn't make these videos. I don't know how to explain as I'm going. I can't think and talk at the same time. I'm just that's not how it works. Okay. So in this case, I'm gonna try. In this case, they don't overlap in Y, right? So, uh, oh no. Okay, so now they do overlap in Y, right? Is what we have here. Um, okay, all that just gets us to this case we actually care about where they overlap. Yeah, okay. So now they definitely overlap, and I've taken us down to the case where um, the upper left, the top upper left corner of B is inside the A cuboid, right? In which case, um, we in which case we break the B cuboid into, okay, and we're not subtracting, we're adding here. It's going to be a similar function. So then we're going to break it into, okay. Okay. B equals, so we're going to start at the bottom left corner of equals A1 to B1, right? Okay, and then we have 3 strips. Maybe we should have a function to test whether something is empty. Yeah. But then we have 3 strips from 3 additional cuboids that go from B0 so from A0 X no, A1 X Y starts at B0 Y Z starts, so but I don't I don't know what Z is because I can't draw it. Let's I don't know, so let's leave that for a moment. And it goes to B1 X goes A1 Y Z. I still don't know how Z works. So that's one of the 3 that we will be. Okay, so now we can return A. Do we need we actually don't need all those strips. We only need we could have consolidated two of those 3, but not all 3. So now wait, 1 A those, and then Okay, so the first one started there. The second one starts at b0x. And a1y. a1y. And continues to well, okay, just to show you it's not like I have a clever diagram. I'm just looking at two things that overlap with each other. Oh, I'm doing very badly at this today. So it goes down to the x stays the same. No, the x goes to a1x. And the y goes to b1. b1y. Right? Okay. Now, and I can't figure out this third one until I figure out how the third dimension works, so we should plug in our z's, right? And actually, are there 3 strips or are there 4? Oh my god, that's how badly I'm doing at this. I wish I had a cube. I don't even have anything cubical. So if you've got cube here, you've got 3 by 3, 2, 1, 2 cube, 2, 2, 2. Yeah, I think there are just 3 strips. So I don't even know if this is the right representation. Would an easier way to do it just to be to punch the 2 holes out of it? Yeah, to make a union and then say, or a compressed. Maybe we should go back to a. Now I'm just being indecisive. See, we could. It might be straightforward. As opposed to doing all this clever geometry, we could just come up with a way of compressing ranges in the previous case. I think that's going to be easier to debug, to be perfectly honest, because I think we can get there on this, but it's going to be a huge problem. So let's so okay, so what is this? All of this stuff can go. Okay, so we're not actually going to be iterating over any of this stuff, but let's think it through. So we know all these ranges, and we want to insert numbers into that range. So let's think about this not geometrically, but just algebraically. So this can be it amounts to the same thing though, doesn't it? Because it's three-dimensional ranges. Let's split it up into okay, we could have a bunch of x ranges. So we could have a bunch of integer pair x ranges, and each of those carries along with it a bunch of y ranges. And each of those carries along a bunch of z ranges, right? Okay. Okay. So for x start what, did I really not do this? Okay. If x, okay, x begin start forget it. I'm futzing because I don't want to think. Um, okay, then we do need to go into this. Okay. Oh no. Oh. I'm coming up with very complicated ways to do this because we have to break that X range down, but we only have to break it down in places where these things overlap. There's got to be an easier way to do this. I've taken an hour at this, and I still don't have a strategy. Well, I have strategies, but they're all very complicated. Or at least I'm thinking about them. I haven't found a simple way to think about the strategies. Come on. One dimensionally, what do? We have ranges, they overlap. There are three possibilities. What you can have a range. The second range can be entirely disjoint. It can partially overlap, or it can be entirely within it. Right? Three possibilities. Outside, overlap, inside. If you're adding these two things, the first and the third cases are trivial because yeah. Okay, so it's easy in one dimension. In two dimensions, you have a cuboid, right? You have a squareoid, a rectangle, as we say. So you can either, let's assume that we take the one to the left. You can have something entirely disjoint. You can have something that intersects with you on top like that. You can have something that intersects with you on top and to the right. You can have something that intersects top and bottom. You can have something that intersects just bottom. You can have something that intersects bottom and right. So you can have it leave the top, right, and bottom. So there are three bits. 1, 2, 3, 4, 5. If there are 3 bits, how did I get 5? Top, bottom, and right. You can have top, bottom, and right. Oh yeah, so there's one. Yeah, you can have it on the right, but not the top or the bottom. that's 1, 2, 3, 4, 5. 6, 7. It can be none of those, so it can be in the middle. 1, 2, 3, 4, 5, 6, 7. And 8. Yeah, okay. Okay. So top, right, and bottom, because there are that many faces. Oh. Whereas, because you can eliminate one face with the XX, so if you do that, then there are in 3 dimensions, because instead of 3 faces, there's 6 faces. So there are 5 bits, right? So there are 32. I'm not going to think through all 32. I need a way that just deals with them. All 32 ways to intersect. Oh, we're nowhere on this. It's 11:05 and we're nowhere. God. And we only have a few hundred of these damn cubes. It's not that complicated. 30,000 times 20,000. Um, so oh, I've never done these stupid geometry algorithms. I was actually asked this in an interview once, a thing in an interview once related to this, and I did figure it out. But like these UI people clearly do this all the time, and I'm struggling to derive it from first principles. I mean, I don't even know how to search for a point in 3 dimensions. How do you do that? You just and I mean, we could figure out what the which of the 30, but with 32 intersections, we're not going to think through 32 different ways of overlapping. Um, it's just not going to happen. And there are too many points to. Yeah, just the one. Okay. Oh. Well, this is the first one I'm genuinely tempted because I really have made no progress on this. I'm genuinely tempted to just, call it a night and hope I'm smarter in the morning, which I usually am. Um. Oh. I really got my interest is waning. We just want to count the number of lights that are on, right? How many cubes are on? So what we really want to do is, okay, I think my first approach was right. So we want to go through. We want to have a set of cubes that are on, and every time we have a new cube, we want to be able to either add or subtract a cube from existing cubes, and that means breaking up the existing cubes into a collection of non-overlapping cubes, right? So what's the best way to do that? So if you have two squares and you know they overlap somehow, whichever one is to the left, right? You know they overlap somehow. So you break it into the bits of the first one that are entirely to the left. Yeah, there are parts that are, for any two cubes, there are parts that are to the left, to the right, the top, bottom, do. Okay, so given two cubes, let's write that down. Let's just go. Okay. So, okay. So, deconstruct. Okay. And that will give us let's name them. Just as an array of cubes. Just B. If we can write this function, we can do it, right? So okay, So, um, um, or, oh, yeah. Come on. Okay, so okay, and we can okay, just a um, and we can break that into 27 27 regions and just see which of the right because any two cubes um how did I say there were 32 ways to overlap but now I'm saying there are only 27 regions um well okay there is do okay so um okay so we can if we generate 27 cubes here um I'm just not in the mood to do this today um yeah you know what um I'm not having fun. So I'm gonna take a second look at this in the morning, and I apologize for letting you down. But yeah, I'm gonna take the night off and come back at it in the morning. So anyway, maybe I'll post something then.